Hello and welcome to Electromagnetics 1. Chris Trampel here. The topic of Lecture 3 will be differential vector calculus. Well, why do we need differential vector calculus? As we saw in the first lecture, Maxwell's equations can be written in differential form in terms of curls and divergences. And therefore, we need to understand differential vector calculus based on essentially third semester calculus that you took. Maxwell's equations also can be written in an integral form, so we'll also need to understand integral vector calculus as well. One of the goals, the big goals of this course is I'm hoping that as you learn to solve Maxwell's equations for various geometries and in various situations, you won't always have to resort to the mathematics. In other words, what we like to have is some kind of an intuitive expectation about what the fields should do in a particular situation before we even go ahead and solve the equations. That's a challenge, but you develop that intuition largely by solving a lot of problems, seeing a lot of different situations, a lot of different geometries, a lot of different excitations, and so forth. So as we go through the course, just be thinking about what you expect the fields to do in a particular situation, even before you dive into the mathematics. But we do need the math to make these field predictions precise and quantitative. Well, what exactly is a field? A field is a function that specifies a particular quantity everywhere in a particular region. So for instance, we have two basic kinds of fields, scalar fields and vector fields. In the case of scalar fields, a good example would be the temperature in this room. For every single point in this room, I can assign a temperature value. And that's really all a field is. It just takes a region of space, and for every single point in that region of space, it assigns a number, in the case of a scalar field. In the case of a vector field, you take every single point in a region of space and you assign a vector to it. So at every single point in this room, if we were looking at the gravitational force or something like that, we could assign a vector that has a magnitude and a direction. The magnitude telling you the strength of the field in that direction, and the direction of the arrow telling you which way that force is acting. So we're going to be seeing and using both scalar fields and vector fields in this course. Now, the electric field is a vector field and the magnetic field is a vector field, but oftentimes we're going to be able to simplify things such that we can get the electric field or the magnetic field from a scalar field, and we'll see that later in electrostatics. Well, if you remember in first semester calculus, they introduced the notion of the derivative, and the derivative was defined on the real number line. In other words, it was defined in one dimension. Well, in electromagnetics, oftentimes we're working with 2- or 3-dimensional geometries, and so we need essentially a 3-dimensional analog to the 1-dimensional d by dx that you learned about in Calc 1. And that's what the derivative, or that's what the gradient is. Excuse me. The gradient is a vector differential operator that, when it operates on a scalar, results in a vector. Okay. But it is those two things. It is a vector differential operator. So if you'll notice here, so we can write the gradient operator in Cartesian coordinates like this, and it has derivatives in it. That's the differential part, and little unit vectors, x hat, y hat, and z hat. Okay. In cylindrical coordinates, the gradient takes this form, and in spherical coordinates, it takes this form. In your text, you'll be able to reference these. In other words, they're in the back of Satiku, if I remember correctly. So you don't have to memorize them, but you do need to have to recognize that if you're working in Cartesian coordinates, you need to use this definition for the gradient. If you're working in cylindrical, you need to use this. And if you're working in spherical, you need to use this one. Well, what physically, again, going underneath the mathematics here, what physically does the gradient of a scalar field tell you? I mean, if I have some scalar field here, v, which is a function of x, y, and z, and in other words, it's a function of the 3 Cartesian coordinates, and if I take the gradient of that field, well, what am I getting? And it turns out that the gradient of a scalar field, v, is a vector that represents both the magnitude and direction of the maximum spatial rate of increase of that vector field, v. So when you take a gradient of a scalar, you get a vector here, g. So the gradient of v in whatever coordinate system you choose will be a vector g. Okay, and that vector points in the direction of maximum increase of the field at that point. And the direction of g is going to change depending on where you are in space. But another way of looking at that is if you want a little differential change in the scalar field here, you just take the gradient g dotted with dl. If you look at this diagram here, dl is just a vector that points in a particular direction. You'd like to know how quickly is the field changing along this direction at this point, and the answer is g dot dl, or the magnitude of g times the cosine of the angle between the vector of interest and the gradient. And you can see very cleanly here that this differential scalar field here, dv, is going to be maximum when cosine of theta is 1. That happens when theta is equal to 0. So when this angle goes to 0, in other words, when you are marching along or you're walking directly along the direction of the gradient, the rate of change here, dv by dl, is maximized. So that's how you understand that the gradient is telling you the direction of the maximum increase of the scalar field at a particular point. Well, it turns out we can also cook up some operators using the gradient to operate on vectors as well. One of the most important operations we will be doing with the gradient is the divergence. Okay, taking the divergence of various vector quantities. You'll see these directly, this sort of expression directly in Maxwell's equations. In Cartesian coordinates, the definition of the divergence is the following. Again, it's a differential operator that operates on a vector with a dot product in between it. Okay, so you can see what you do to take the divergence of A is you simply take the partial derivative of the x component of A with respect to x, and you add that to the partial derivative with respect to y of the y component plus the partial derivative with respect to z of the z component. Okay, so the operation of the dot product on a vector results in a scalar. Okay, just to give you some intuition of what the sign of the dot product will be for various kinds of fields, have a look here at figure 315. If you notice, if this is what the fields are doing here at a particular point, say point P, if this is what the vector field looks like, this particular vector field is going to have a positive divergence. We'll talk about this later when we talk about the divergence theorem, but you can think of putting a little spherical surface around this point and imagining that all of these rays, in a sense, are diverging outwards from this point. That's considered positive divergence. if you'll notice here, this vector field are diverging on the point. That's considered negative divergence, and you can see that the fields in a sense aren't spreading out here at all. For example C, that's an example of a field with zero divergence, with no divergence at all. There's a second operation that we can use the gradient with, and if we combine the gradient with a cross product, and it will act on a vector and it will generate a vector. So the dot product acts on a vector and gives you a scalar. The curl acts on a vector and gives you another vector. Okay, and this is usually how I calculate the curl when I'm doing it at least in Cartesian coordinates here again. And you definitely want to reference your book again for the curl in cylindrical and spherical coordinates as well. But in terms of Cartesian coordinates, this is how you set up. There's a little matrix that 3x3 matrix that you can set up here, and then you just simply take the determinant of that matrix to figure out what the curl of A is. And this is how it breaks down. You can satisfy yourself that this expression here is in fact the divergence, or I should say the gradient of the determinant, excuse me, of this little matrix, which is a vector. Well, just to summarize here, the gradient of a scalar gives you a vector. The divergence of a vector gives you a scalar, and the curl of a vector results in another vector. So just these are things you just need to understand again, so you have some expectations. Okay, well, what is the quantity? Is it a scalar? Is it a vector? What am I operating on? A gradient with it on? Is it a gradient? Is it a divergence? Or is it a curl? And what kind of quantity should I expect coming out? Well, just like in first semester calculus, in first semester calculus you had the notion of a first derivative with respect to x. Similarly, you also defined the notion of a second derivative, a third derivative, higher order derivatives. In other words, it turns out that in electromagnetics, we also need essentially three-dimensional versions of the second derivative. So if the gradient is the three-dimensional analog of the first derivative, then we've got a number of notions of second derivatives with respect to space in electromagnetics. Okay, if you take the gradient of a scalar here, remember this will result in a vector, and so you can operate on that vector with the dot product. And it turns out that if you take the divergence of the gradient of a scalar field V, you get an operator here that we refer to as the Laplacian. Again, think of it in terms of it's very much like the second derivative. The Laplacian is the most like the second derivative for a three-dimensional field, okay? Because it results, the output of the Laplacian is a scalar field here, of the scalar Laplacian, at least in this case. All right, and this is the definition of the scalar Laplacian in Cartesian coordinates. Again, check out in your text for the definitions in cylindrical and spherical. Okay. There are some nice properties here of gradients, curls, and divergences that I want to mention. The curl of the divergence of any scalar is always 0 here. This property, anytime you take a gradient and then take the curl of that resulting vector, you're going to get 0. It works out that if you first take the divergence, if you sort of change the order of operations here, first take the divergence of A, that's a scalar, and then operate on that scalar with the gradient to get a vector. That's just simply a way of stating that if you flip the order of operations here, instead of getting a scalar, you get a vector. Another property that always works, you can always use this when you're manipulating equations, is the fact that the divergence of the curl of any vector, no matter what it is always 0. Okay, so there's some theorems that are built on this, and we'll talk about those later. But what this is saying essentially is that after you've taken the curl of a vector, that remaining field has zero divergence all the time. This is an important identity here. The curl of A it can be written like this: the gradient of the divergence of A minus the vector Laplacian of A. Okay, and the vector Laplacian here is just simply defined as the scalar Laplacian operating on each component of the vector. Okay, so you have to, in order to tell whether it's a vector Laplacian, as in this case, or a scalar Laplacian in this case, you just need to look at the context. If you're operating on a vector with a Laplacian operator, by definition, it has to be the vector Laplacian. Okay, well, as I alluded to before, there's some interesting physics underlying the fact that the divergence of the curl is zero. Okay, and it turns out that we can actually use the curl and the divergence to classify different kinds of vector fields. All right, vector fields are uniquely defined by their divergence and their curl. However, neither the divergence nor the curl alone of a vector field is sufficient to completely describe it. You have to specify both the divergence and the curl of a field to get a unique field. There are 4 examples here that are shown in your text that I want to go over. If you have a vector field that looks like this, which is basically it points in the same direction everywhere in space and the magnitude doesn't change, okay, that field has no divergence and it has no curl. All right, both the divergence and the curl of a field that looks like this will be zero. However, if you look at example B here, this is a field that points radially out, no matter where you are in space, and whose magnitude does not change. Okay, it turns out this kind of a field has non-zero divergence and zero curl. If the curl of the field is zero, it's called irrotational. So this is an example of an irrotational field, and it kind of makes sense, right? No rotation, that nothing is rotating around this center point here. It's all just radiating out. That's to do with divergence, not with curl. The opposite situation here, this is this field is sort of pointing in like the negative phi direction if we're in cylindrical coordinates here, and the magnitude is constant everywhere in space essentially. This field has no divergence, but it has a non-zero curl. So if the divergence of a vector field is zero, we refer to it as solenoidal. So this field here that's just sort of wrapping around but not changing in magnitude as you move is an example of a solenoidal field. And in general, for a general vector field, we don't expect that necessarily the curl will be zero or the divergence will be zero. We simply don't know. And that kind of a field that has non-zero divergence and non-zero curl is shown here in letter D. Well, there are 3 foundational theorems that I want to introduce here that relate to the characterization or classification of vector fields that we just saw. The first one is called the IRrotational Theorem. That's what I'm calling it anyway. And it basically says the following: let a vector field B, or let B be a vector field. If the curl of B is zero, then there exists a scalar potential field, in other words a scalar field, psi, such that B is equal to the gradient of psi. Okay. Let me give you an example of this. Okay, I'm going to switch to the overhead momentarily here, and we'll talk about what it means to have a field that has, in this case, no curl. Okay, the curl is 0. In other words, irrotational. So here's an example of, find myself here on the screen. Irrotational vector field. Okay, let's look at this particular vector field as an example here. Let's say that in this case our B, our original field, was just simply equal to rho hat. Okay, so remember from the coordinate systems lecture here, if we're in cylindrical coordinates, the rho hat, no matter where we are, the rho hat vector points radially out. So at this point, rho hat is pointing radially out in that direction. At this point, it's pointing in that direction, and so forth. It's just always normal to the surface of a circle, right? This is the rho hat direction. Okay, just like that. So basically, that's what this B field looks like. It just looks like this. It always points straight out, no matter where you are, and the magnitude is always the same. Okay, the magnitude isn't changing. The vector field B is always just pointing radially out, just like that. Okay. I claim that B is irrotational, which is to say that its curl is equal to 0, but I need to prove that. I need to show that, in fact, this particular field has no curl. I mean, just kind of by looking at it, again, there's no rotation around the point, so we kind of expect that it is, in fact, an irrotational field. But let's prove it mathematically. Okay. So look, if you go to the back of your text, you'll see a definition for the curl of a vector in cylindrical coordinates, and it looks like this. This is how you take the curl in cylindrical coordinates here. 1 over rho partial of the z component of B with respect to the phi direction minus partial of the phi component of B with respect to z. That's in the rho hat direction. Slide up a little bit here. Plus the partial of the rho component of B with respect to z minus partial of the z component of B with respect to rho in the phi hat direction. Okay, remember, the result of the curl operator acting on a vector is going to be a vector. So that's where these little vectors are popping up here. Plus 1 over rho partial with respect to rho of rho times the phi component of B minus partial of the rho component of B with respect to phi in the z hat direction. Okay. So you got to know what coordinate system you're in order to pick out which version of the curl, which definition for the curl that you'll need. Okay. All right. Now we want to apply this definition to this particular example of a B field here. This is what we want to apply this definition to this particular vector field B. And it turns out that the only non-zero component of this vector field is the rho component, which is equal to 1. Okay, it's just the coefficient here of the rho vector. So in this case, B sub rho is just equal to 1. So if we look down in here, BZ is 0, B phi is 0, BZ is 0, B phi is 0. The only two pieces here that are potentially non-zero are this one, because B rho is 1, and this one here, because B rho is 1. But in this case, the partial derivative of 1 with respect to z is just 0, okay? The partial derivative of 1 with respect to phi is 0. So in fact, for this particular vector field, the curl of B is in fact 0, okay? So therefore, this is an example of an irrotational vector field. And what the irrotational theorem says is that since the curl of B is equal to 0, there exists some potential function psi such that the curl of psi is equal to B. In other words, this implies that there exists a psi such that B is equal to the curl of, I should say, B is equal to the gradient of psi, excuse me. If you go back here and look, yeah, B is equal to the gradient of psi, excuse me. B is equal to the gradient of psi. There we go. That's what I meant to say. This makes sense dimensionally, right? Psi is a scalar. The gradient of a scalar gives us a vector, okay? Let's see if we can figure out what we should choose for psi such that the gradient of psi is going to be equal to our B, which is rho hat. So in other words, we want to find a psi such that B, the gradient of psi, will be equal to rho hat. All right, that's what we want to find. Okay. Well, if you look at the gradient operator now in cylindrical coordinates, the gradient operator in cylindrical coordinates takes a particular form. Just a second here to restart my camera. While I'm doing that, I will find the definition for the gradient in cylindrical coordinates. As soon as this fires back up, I'll show you from the textbook what the definition is. Okay, great. Zoom in a little bit here. Okay, let me show you this definition here, and this is from the back of, let's see, I'm going to focus this a little bit here if I can. Just a moment. Focus this for you. There we go. It's going to find it. Okay, very good. So here we are in cylindrical coordinates, and this is the definition of the curl that I showed you, and here's the definition of the gradient, all right, in cylindrical coordinates, all right. And if you'll notice, again, we've got the derivative with respect to rho in this case times rho hat, 1 over rho times the derivative with respect to phi times phi hat, and the derivative with respect to z times z hat, okay? So in the context of our problem, we need to come up with, again, a psi such that when we operate on it with this operator, we're going to get rho hat, all right? So let's try as our candidate, autofocus here again, let's try as our candidate here for psi the following. Let's say, again, we want, let's choose psi is equal to rho hat, okay? Then since the gradient of psi in cylindrical coordinates involves the partial of psi with respect to rho in the rho hat direction plus a number of other terms that are equal to 0, the partial of rho with respect to rho is just simply equal to 1. So in fact, it does work out. The gradient of this particular psi, rho hat, is equal to rho hat, which is equal to b. Okay. All of this is simply to say and simply to show you that if you have an irrotational vector field, you can, instead of working with a full vector, you can work with a scalar field instead. And then at the end, you can just take the gradient of that scalar field to get back to the original vector that you want. We're going to take advantage of this in electrostatics. And this psi is going to become the electric scalar potential, or voltage V. So we're going to use this theorem in electrostatics. But this is why it works, is because of the irrotational theorem. Okay, coming back here just momentarily. There's a second theorem that, no surprise there, is the second. If there's an irrotational theorem, there's probably a solenoidal theorem, and in fact there is. And the solenoidal theorem simply says, let C be a vector field. If the divergence of C is 0, then there exists a vector potential A such that C is equal to the curl of A. Okay? Well, again, what does that mean? Let's come back to our Elmo here. What does it mean in terms of something practical? Well, let's look at another vector field in this case. Let's look at one that looks like this. Come down here again. Let's say our vector field, our original vector field here, I'm going to match the names. Let's see here. Okay. Let's say our original vector field C is equal to phi hat in cylindrical coordinates. Okay. So this field would look something like this. This is what it would look like. Now, again, the magnitude doesn't change, but it always is pointing in the phi direction, no matter where you happen to be in space. So this is kind of what C would look like. And it's no surprise to us that a field that looks like this has 0 divergence, right? It certainly doesn't look like anything is radiating outwards. Nothing is radiating outwards like this from this point. It's all kind of literally curling around, okay? And so we would expect this field to have non-zero curl and 0 divergence. But again, we have to prove it, okay? We have to prove it. If you look again in the back of your text, I'll show this again. They have the definition of the divergence here in cylindrical coordinates right here. This is the definition of, I'll focus just for a second here. This is the definition of the divergence right here in cylindrical coordinates. 1 over rho, partial with respect to rho of rho times the rho component of A plus 1 over rho times derivative of respect to phi of the phi component plus the partial respect to the z of the z component. All right. So we have to show that in fact this field here, C equals phi hat, in fact has 0 divergence. So I'm just going to, the divergence is simpler, so I'll write that up here. So divergence of C is going to be equal to 1 over rho partial with respect to rho of rho times the rho component of C plus 1 over rho partial with respect to phi of the phi component of C plus partial with respect to z of the z component of the vector field C. Okay, so in this case, for this particular vector field, the only non-zero component is the phi component, which is equal to 1. All right, so this term goes away, this term goes away, and the derivative of 1 with respect to phi is in fact 0. So that implies that the divergence of this particular vector field is in fact equal to 0. So therefore it is solenoidal. This field is completely solenoidal. All right. Okay, well, what does that mean we can do based on the solenoidal theorem? Just coming back here for a second, it says that if the divergence of C is 0, it is, there exists a vector potential A such that C is equal to the curl of A. Okay. Well, again, going back to the definition of the curl that we saw beforehand in cylindrical coordinates, the question is, what kind of an A can we come up with such that C is equal to the curl of A? The solenoidal theorem guarantees that this A exists. It's out there. The question is, can we write it down? And a good candidate for this guy, let's try A is equal to Z rho hat. All right? And then we'll take the curl of this guy, all right, and we'll see if the curl of A is in fact equal to C, which is phi hat, all right. Going back again to the definition here of the curl in cylindrical coordinates right here, let's look and see if we can pick out and figure out which of these pieces is going to be of interest for the particular C that we've chosen. It only has a Z component, right? This guy right here, A is equal to Z rho hat. It only has, it only has a rho component. Everything else is 0 in this particular case. So this term is 0. There's no Z component. There's no phi component, so that's 0. That piece is 0. That piece is 0. And so the only possible non-zero terms are right here. The partial derivative of the rho component with respect to Z and the partial derivative of the rho component with respect to phi. Well, the partial of Z with respect to phi is 0, okay? But the partial of Z with respect to Z is in fact 1. So the curl of this guy, it all boils down to simply being equal to the partial of Z with respect to Z in the phi hat direction, which is just equal to 1 times phi hat, which is just equal to phi hat, which is, in fact, equal to C. Okay? So, long story short here, these two theorems, the IRrotational theorem and the solenoidal theorem, are really powerful because they allow us to simplify some things. If the curl is equal to 0, then we can find a scalar such that the original vector is equal to the gradient of that scalar. If the divergence is equal to 0, we can find a vector, in this case A, such that the original vector is equal to the curl of that vector. Okay. There are situations where that's really a useful property. It's something that you'll need to understand. Putting those two theorems together, the IRrotational theorem and the solenoidal theorem, we have what's called the Helmholtz theorem, which says that any physically realizable vector field D may be decomposed into the sum of an irrotational and a solenoidal vector field. That is, D may be written as B plus C, where the curl of B is 0 and the divergence of C is equal to 0. Okay. So again, we're going to use these three theorems to write fields in advantageous ways for us throughout the course of this class. Well, thank you for your attention, and I'll see you in the next video.